So it turns out that there's a deep connection between the undirected graphical model and statistical physics. In particular, we use a model known as the Gibbs distribution to model the joint probability distribution, and which this Gibbs distribution was originally used in statistical physics to model random motion of the particles in Brownian motion, and it is given by this equation over here. So we can see that this expression over here, it exactly fits the joint distribution of the factors that we have used earlier on in our undirected graphical model, where the difference here, or where the addition over here, is this energy term which we use to represent our potential functions. And this is of course brought into an exponential term to constrain the range of this particular energy function. And in this case here, the energy function is always more than 0, hence we term it as an energy that is associated with the random variables in a clique of C. So in the original use in the statistical physics, this represents the energy of a particle in the liquid or in the air, for example, where this particle is randomly moving around. So we will express it using this Gibbs distribution over here, and the interaction, because when this particle is moving around in random motion, in the Brownian motion, there is a certain interaction between neighboring particle, and we will use it we'll use this Gibbs distribution to model this distribution, to model the random motion of the particles in the liquid or in the air in statistical physics. Over here, we adopt this particular representation or this particular distribution in our joint distribution for the undirected graphical model. So we can convert the Gibbs distribution to an undirected graphical model by simply defining the Clique potential over here, or the Clique function over here, denoted as phi of C, where y of C denotes all the random variables in the Clique conditioned upon the parameters of this particular Clique over here to be equals to the exponential term of the negative energy function that represents this particular Clique over here. And this can be directly plugged into the original joint distribution, where this term over here is originally the multiplication of all the cliques in the graph of the potential function of each clique that is parameterized by the random variable in that clique condition upon C. So now we have replaced each particular term over here using this guy over here. And since we are multiplying all the exponential terms together, what this means is that we can bring the exponential product into the exponential to become a sum of all the energy potential. And as a result, we'll use this to represent, we can use this particular expression, which is the Gibbs distribution, to represent our joint distribution in the undirected graphical model. We'll also see that high probability states corresponds to low energy configuration over here. So since in this case over here we have since this is a negative exponential function over here, where this is this distribution, the joint distribution of P of y, and which is given by a negative exponential function over here, where this guy over here is actually the energy function inside this exponential term. The higher energy, the lower probability. And since in this case here it intersects at 1, this means is that we want, if we want a higher probability, we want to maximize the probability over here, then what this means is that it corresponds to the lowest energy that we configuration that we have in the joint distribution over here. And since this is energy based model, we also term this guy over here, phi of C, as a potential function, which I have already been using interchangeably with local function a few slides ago. So potentials represents the relative compatibility between the assignments to random variables. And what this means is that let's say if I want to have looking at a pair of random variables that is linked by an edge over here. Let's call this random variable x1 and x2 over here. So in this case, if the potential of between x1 and x2, which is represented by a energy term, is very low, this means that I would have x1 and x2 in a correct configuration that satisfy the energy function, and this directly corresponds to the maximum likelihood and the inference algorithm that we are going to look at in the future lectures. So a general approach to further simplify this representation is to define the log potential as a linear function of the parameters. We'll see some example in the next slide, where we can simply rewrite this potential, this log potential, because as noticed here that this guy over here, we have replaced it with the energy potential, the exponential of the energy potential. So this is equals to minus E of C, and if we take the log over here, so this simply means that this term over here is equals to the negative energy term that we have seen in the previous slide. So we will directly replace this energy term with a linear function. So this is just a dot product. This is just a dot product of two vectors. So phi here, which we'll call the feature vector, is defined as the feature vector derived from the random variables, directly from the random variables of yc. It's actually a m dimension vector multiplied by m dimension parameter, which is theta c over here. So this guy over here is nothing but just a vector c1 all the way to theta c m over here. So this would become a linear combination of the feature vector and the parameters in theta c, and we'll use this to represent the energy function in the Gibbs distribution that we have defined earlier on. So the resulting log probability will now have this particular form over here. Once we take the log of it, this means that we will be remaining the energy term and minus away the log of the partition function. So in this case, this is also known as the maximum entropy or a log linear model. An example here would be, let's represent this particular graphical model, the undirected graphical model that we have seen earlier using the log linear potential function. In this case, we will represent each clique as a dot product term of the feature vector multiplied by the parameters in the local clique. So this implies that the local potential or the potential function is equals to the exponential of this term over here. And let's now look at the case where the clique of y1, y2 formed by y1, y2, and y3 over here, where we can set m, the dimension of the feature vector as well as the parameter, to be equals to the cardinality of C. So in this case, this guy here would be m equals to 3, because we have 3 random variables. This means that we'll define a parameter vector theta c equals to theta c1, theta c2, as well as theta c3 transpose. This is a vector of the parameter, and also a feature vector as a function that maps the random variables, the state of the random variable y1, y2, and y3 into a m dimension vector over here. So in this case, we can simply rewrite this into a function of c, y1, y2, y3, and the dot product by the parameters over here. So the number of entries over here, the respective entries over here, we can see that it becomes a linear combination of the three parameters based on the current state of y1, y2, and y3. So here, the three-dimensional vector of the feature can be directly the state of y1, y2, and y3. We can see that in the first case here, the vector would be simply 0, 0, 0 transpose. And the second case here, it would be 0, 0, 1 transpose, and so on, so forth. So each one of these would be a unique vector by itself. And then taking the dot product with this data, we would have the desired parameters. So here we can see that if we set m equals to 3, this means that the feature vector would be a function that maps the input parameters or the states of the random variable into a three-dimensional vector. We'll only need 3 parameters to parameterize this distribution table of the Clique potential instead of 2 to the power of 3 parameters. So this can lead to a huge reduction of the number of parameters needed to represent the joint probability distribution. Hence, it will enhance the tractability of the learning and inference algorithm. And it's also possible to combine undirected graphical model with directed graphical model. So what this means is that in a graphical model, it's possible to see both undirected graphical model as well as directed graphical model. An example is given by this graphical model over here to model that map from stereo images. So in this case here, what I meant by that map from stereo images is that in a typical stereo setup, we will have 2 cameras looking at the scene, looking at a particular scene over here. And these 2 cameras, the baseline between, the distance between these 2 cameras are known. So we can call it T over here. And what happens here is that according to the principle of light traveling in straight line, any light that is reflected from a particular point in the 3D scene will end up to be an image point here. And there is also the same reflection that ends up on the image point in the right image in the stereo rig over here. And since there is a certain disparity, there's a certain distance between the 2 cameras setting in the stereo setting, this means that the pixel here and here would be slightly different. This could be called X and this could be called X prime. So we call this a disparity. And according to this disparity plus the triangulation over here of the 3D point, we'll be able to estimate the depth of this the actual 3D point from any one of this camera. So here this is how a depth map would look like if we do a naive triangulation of every pixel from the known translation T over here. And what we can see here is that every pixel here, the intensity represents the depth or the distance away from the camera. The darker it is, the further away the object is in the 3D scene from the camera. And we can see that a naive way of getting the depth map, there is a lot of uncertainties, there's a lot of artifacts that can be observed in this depth map over here. And so what we want to do here is that based on this observed depth map, where every pixel here represents 1 to L, where we discretize the distance from the camera to 1 to L meters away from the camera, for example, and we want to recover back the actual depth map, which is the correct depth map, by enforcing smoothness constraint. Because here we can see that some of the pixels, even though they are neighboring pixels, the depth disparity, the difference between the depth jumps a lot. But in the real world case, is often a smooth transition between the neighboring pixel. So we want to encode this into the depth map, and we want to obtain the real depth map, which is represented by a set of latent random variables. This is the unobserved random variables that we want to obtain from the observed random variable. And what we can do here is that we can represent the latent random variables as what the actual depth that we want to obtain as ys over here, and where every neighboring pixel we enforce a consistency between every neighboring pixel. Hence, it forms an undirected graphical model, a Markov random field in the latent variable. But every random variable here, there is a direct observation of that pixel that is given by the initial depth map that we have obtained from the naive triangulation of the stereo camera. Hence, every random latent random variable, there is an arrow that is pointing towards, because it directly gives rise to this observation that corresponds to that particular pixel over here. Hence, it becomes a directed graphical model over here. And in this case here, we want it to be smooth in terms of the labels. This means that we want to add a prior to encourage smoothness between the neighboring pixels over here. And as a result, we can rewrite this into this term, the factorization over here. We want to model the joint probability of x and y conditioned upon all the parameters, which we call j and theta. And this can be factorized into the parent-child relation of the directed graphical model over here. And this, in this case here, we call this the likelihood term, because this is conditioned upon the latent variable, where x here is our observed random variable. Hence, this is a likelihood term. And we also have a term which we call the prior term over the latent random variable, so of y, which is the random variable that we are not observing. And there is some prior knowledge that we encode inside here. And we'll use an undirected graphical model to model this, because we know that the pixels are arranged spatially. This means that neighboring pixels over here, we want it to take a similar label as much as possible. And here we can encode this using a pairwise potential over here. So this term here is directly from the graphical model. This term here is because we are modeling the spatial context, and hence we use a undirected graphical model over here. And notice that we need to divide by the partition function, because this, in this guy here, is not a valid probability distribution. To make it a valid probability distribution, we need to divide by the partition function, which is the marginalization of all the potentials, product of the potentials over the random variables. So this setting over here can also be applied to binary image denoising, the binary image denoising problem as shown in this illustration over here. Suppose that we are given an image which is corrupted with many salt and pepper noise, for example. So you can see that there are many speckles over here of noise that corrupts this particular image. And this is what we have observed over here, denoted by x. This is a binary state random variable. You can take 0 or 1 in this binary image over here. So what we want to recover here would be the clean image, which we represent each pixel as a latent random variable y. It can also take a binary state of 0 and 1. So in this case here, we will represent the latent variable using an undirected graphical model because of the spatial arrangements of the pixel. So what we want here is that we want two neighboring pixels over here to take the same label as much as possible. Hence, we model this using the pairwise potential, and we will penalize the cost of this potential if the two random variables, the two neighboring random variables, are not taking the same label, and we'll encourage it if they are taking the same random variable. But at the same time, we'll also make sure that the likelihood is followed. This means that we'll also make sure that we observe, since we have observed xs, for example, or xt in this case over here, since we have observed xt, we also want to make sure that the label that we assign to xt does not deviate too much away from xt. So we can see that in the case where if we do not have this term over here and simply encourage the smoothness in the prior term over here, then what would result is that the final image over here would become totally white or totally black. But in the case where we have the unary potential or the likelihood term, where we enforce the final result to be as close to the original given image, although it's corrupted image. We want it to follow it as much as possible to retain the overall content of the corrupted image over here. There are two models. We'll see this in more detail when we talk about the graph cards, that we can use the graph card algorithm to infer this fully, but that would be the last lecture. And we can see that we can make use of the Ising model in the case where we have binary random variables for the latent and the observed variables, which takes the state of 0 and 1. So in this case here, the pairwise potential. So in this case here, we would have to encourage the neighboring random variables to take similar labels as much as possible. And here we'll use the absolute value of ys minus yt. So in this case, if ys and yt, they both take the same label, 0, 0 or 1, 1, then we can see that this term here is 0. What it means is that we'll give it a very low energy value, and this is what we want to encourage. In the case where ys and yt takes different label, 1, 0 or 0, 1 over here, we can see that this term here, the energy term over here, would becomes j, where j is more than 0, and this makes the energy value high, and this is what we want to discourage. So in the case where we have multiple labels, for example the depth map estimation, we want to use the Potts model to model the multi-class label, where the random variable y and x takes one out of L labels over here. So in this case, it will be quite similar to the Ising model, except for we'll take a mean of this the difference, the absolute difference between ys and yt, and 1 over here, to encourage the two neighboring pixels in taking the same label. So it turns out that although we cannot preserve conditional independences when we convert between directed and undirected graphical models, as we have seen earlier, it turns out that we can preserve local probability distribution from a directed graphical model to an undirected graphical model. Suppose that we are given this directed graphical model over here with 6 random variables. We can directly convert the joint probability distribution into the undirected graphical model, where we'll simply use every conditional probability over here in the original directed graphical model and assign it to a potential function over here, that is a function of the random variables in the local conditional probability. For example, x2 conditional upon x1, which represent this guy over here, this arrow over here, and this guy over here. We can directly convert it into a local clique over here between x2 and x1, and we'll simply use this probability distribution table as the local potential function of between 1 and 2, the random variable x1 and 2. Similarly, we can represent all the other random variables, the edges, and convert it into the potential function. But notice that in this case here, the conversion does not guarantee the preservation of the conditional independences. In fact, some might be lost and some new ones might arise. And here, we'll do this for every local conditional probabilities to convert it into the local potential functions. And the final partition function over here can be simply equals to the probability of 1, the marginal probability of x1 over here. And what's interesting over here is the head-to-head structure of x6 over here. So there are two arrows that's pointing towards x6 from x2 and x5 over here. In the context of the local conditional probability, we will get the probability of x6 condition upon x2 and x5 over here. And when we convert it into a local potential function, it will be a function of x2, 5, and 6, where we do not distinguish between the direction of the arrows because there's no more arrows in the undirected graphical model. And what this also means is that we will be interacting, there will be interactions between the 3 random variables after we have converted into a local potential function over here. And this corresponds to a clique here. that we have represented after the conversion. And this brings us to the concept of moralization, where we marry all the unmarried parents of a node from a directed graphical model. So in this particular case over here, after we have converted it into a undirected graphical model, we will marry all the parents, all the unmarried parents in a directed graphical model. So in this case, we have the random variable x6 with two parents, x2 and x5. After the conversion, we'll simply add a link between the unmarried parents. In general, if we have a random variable which we call xi and all its parents over here, so regardless of how many parents it has, after the conversion, we'll simply marry all the parents, which means that we'll simply join out all the links between all the parents. We have a dense connection between all the parents over here, and this is called moralization. This process preserves the joint distribution as we have seen in the earlier slide, but the conditional independences are lost. And we'll also see in the next lecture that moralization is an important step for exact inference, especially when we do belief propagation and message passing in the next lectures. So now let's talk about the difference between the discriminative and generative model. In a generative model, it's an approach that explicitly or implicitly model the distributions of the inputs and outputs. So, and sampling is from the distribution is possible to generate synthetic data points in the input space. And this corresponds directly to the likelihood distribution, where this likelihood distribution can be actually a Gaussian distribution. Here, we can actually sample from this Gaussian distribution. This means that according to the probability, we can sample the random variables from this particular distribution over here. And this is the likelihood distribution. Another advantage of doing this is that we can actually express this as the Bayes theorem, where it allows us to incorporate this prior knowledge of the classes of the latent random variable C over here. And because this can be rewritten into C condition upon X equals to the probability of X condition upon C multiplied by the prior knowledge of C divided by, of course, the marginalization of Px, Pc, and Pc over here. So in this case, we can add a prior term into our distribution when we want to get the posterior distribution over here. And in the discriminative model, it's a model that directly models the posterior term over here without going through the hassle of representing the likelihood distribution as well as the prior distribution. An example here is a regression model, which will allow us to fit a curve, for example, to the distribution. Let's say that I have two classes. C can be equals to class 1 or class 0, for example. And I have many observations of these points over here. So in this case here, there are many, suppose that we are living in a two-dimensional space, X and Y over here. And this represents every point in this X, in this vector X over here. So if we observe all these observations over here, we can see that all these observations here can be clustered into two clusters of class 1 and class 0, for example. And then what we can do here in order to model the posterior of this distribution, we can simply fit a hyperplane or a plane to this to separate the clusters, to divide the clusters into two parts. And this means that by modeling this curve over here, the hyperplane over here, it will correspond directly to our posterior distribution. And in this case here, we will not be able to draw any sample nor to add in any prior knowledge about the class. And we'll simply, because we are simply doing regression fitting to what we have observed. We'll look at more of this discriminative versus generative model when we talk about we will talk about this variational autoencoder in the future lecture. But now let's look at discriminative model, which is also known as the conditional random field. Notice that this is similar to the Markov random field, where both of them are undirected graphical model, with the difference that we are modeling the posterior distribution here directly, which is conditioned upon the inputs x over here, the observed inputs, which we denote as x over here. So here in this case, we'll see that the potential is directly a function of x, where x here is our observed random variables, and w here represents the parameter of the Clique potentials. Here, the partition function is also a function of the observed inputs, as well as the Clique potential parameters. We'll usually assume a log linear representation of the potential, as what we have seen earlier, and with this particular expression over here, where phi, y, c, and x is a feature vector. But now, instead of deriving this feature vector function from purely the random variable itself, we will also use the global inputs of x to model this feature vector, and wc here is the parameters. So the advantage here is that we do not waste resources in modeling things that we always observe. So since we already observe x, we'll use x in the parameterization of the joint distribution function directly. We do not throw away this information when we do inference. We can also make the potential or the factors of the model be more data dependent. We'll see in later example that how is this useful when we know all the data, when we take all the data into consideration when we do inference. It will prevent us from making the wrong inference. The disadvantage here is that you need labeled data for training. So this means that we need all the possible outputs in order to do the learning of a conditional random field, and the learning is of course slower of a conditional random, because now it's taking into account all the observed inputs. A classical example of conditional random field is the naive Bayes classifier, which has previously seen, but in that case we have seen that it ignores the dependencies among the observations. So here in the naive Bayes classifier, we assume that x1 all the way to xn, which are our observed random variables, it's conditionally independent given y over here, and hence we can factorize it into this particular form over here, and we predict using Bayes rule over here. This should be a small y over here, and which we predict using the Bayes rule as denoted by this expression over here. But what we have ignored is the dependencies between all the observed random variables x, which can be important because the dependencies of x can give us a global context of, for example, whether the email is a spam or not, because it's unlikely that every single word in the email is independent of each other. There's a global context that is missing if we treat all the individual words independently. So in the conditional random field, we'll model the full dependencies among all the observations x1 to xn. Hence, we'll end up with this particular undirected graphical model over here, where y is again linked to all the observations x1 to xn, but now we'll also add the edge between all the possible observations x1 to xn. It becomes a fully connected graph over here, and as a result we will get this particular joint probability distribution function where the potential function y conditional upon x and w can be represented as the log linear form over here. So in this case, the feature vector would be a function of y and all the observations x, and the dot product with the w, which is the parameters of the joint probability distribution over here, divided by the marginalization of over y, and this is which is the partition function over here. So this is another form of log linear model over here. In this case, we represent x here as the vector that represents all the random variables x1 to xn, but this can be simply rewritten into individual terms over here, and it simply becomes, because this is a dot product, so it becomes a linear combination. It becomes a summation over the n number of random variables of this product between the feature vector and the parameter itself. Now, for email spam classifier, where we have mentioned in the previous lecture, we denote y to be a binary random variable which can take a state of 0 and 1. So here we can define the feature vector of the product of the feature vector with the weight equals to an indicator function of that y equals to 1 over here. So in this case, y plus means that this is going to be equals to 1. And similarly, if y equals to 0, that means that the email is not a spam. Then we will use the indicator function to represent y minus over here. It's also equals to 1 when the email is not equals to a spam. And multiply by xn over here, where xn is simply the observation of the nth random variable in this conditional random field, multiplied by wm plus, where wm plus here represents the parameter that corresponds to an email which is a spam, and wm minus represents to the parameter that corresponds to the email which is not a spam. As a result, by substituting this back into the joint probability distribution, we get the probability when y is a spam. So in this case here is equivalent to y equals to 1 condition upon x. And we'll get this joint distribution here where it's equals to w plus transpose of x, because we mentioned that when y equals to 1, which is equivalent to y plus, then this term here becomes 1. So we can simply only take these two terms into consideration over n number of random variables which we observe, and this will become a dot product of this y plus term multiplied by x. And it's normalized by the normalization, which is the sum over all possible states of the this latent random variable y over here. Hence, we need to take into account the positive terms as well as the negative terms when y equals to 1 and y equals to 0. So dividing throughout by the numerator, we'll get this particular term over here, where w prime is what we define to be w plus minus w minus. As a result, there's only one set of parameters that we need to learn over here, which is w prime. We collectively call this difference over here w prime, and we don't care about modeling the respective w plus and w minus in the original expression. And now what happens here is that after doing this, we can see that this term over here is equivalent to a logistic regression. So this becomes a sigmoid curve in this particular case over here, where after learning this particular distribution, the joint probability distribution over here with py condition upon w and x, we can directly use this joint distribution. This is the sigmoid curve that we have learned, and z here we have seen it's a function of w and x. It's a function of the parameters that we have learned as well as the observed parameters over here, the observed random variable over here. So given a certain observation of the random variable, we can directly input into this logistic regression over here, and if the probability is more than or equals to 0.5, then we can say that since this is plus over here, if the probability is more than or equals to 0.5, then we can say that the email is a spam given all these particular observation. And if it is not more than 0.5, then we will say that it's not a spam. And here is a very classical example where we can see that we model the probability distribution over here, the posterior probability distribution over here, using curve fitting, where we simply fit a sigmoid curve that is represented by this distribution over here to the observation that we have from the email. And this becomes a decision boundary, as I have mentioned. So in higher dimension, where X is 2-dimensional, we can see that this decision boundary corresponds to this curve over here, this very nice curve over here. And what's interesting over here is that in the case where the dot product term, the linear dot product term, which is essentially a linear combination of w and x, it becomes a nonlinear function. If we replace this with f of x and w, then this whole thing here becomes a deep neural network where f here is simply the input multiplied by the weights that is represented in the in each layer of the deep neural network, and the sigmoid function over here would be equivalent to the activation function, the nonlinear activation function in the deep neural network. Here, if the sigmoid function is replaced by a softmax function, then this neural network can be used for multi-class classification. We'll now see an example on the usefulness of a conditional random field, where essentially we model the relation between all the observed random variables over here. So in the case of a linear Markov chain or hidden Markov model, which we will actually talk about the detail in one of the lectures later on here, where each one of the latent random variable y1 over here forms a linear Markov chain, and every one of these latent random variable give rise to an observation x1, x2, x3, and xt, for example. So in this case here, it's a directed graphical model, which we can use the parent-child relation to write down the joint probability distribution of x and y, which is given in this form over here. And here, in this case, is a generative model because we have a likelihood term over here, which we use to model the observation condition upon the latent random variable. And we can directly convert this into a chain structure Markov random field by replacing the directed edge with a non-directed one. And in this case, we can see that in this particular case here, we can see that the joint probability distribution can be rewritten as the product of all the local potentials denoted by phi y and x, as well as phi yt and yt plus 1 over here. And again, this is a generative model because we can see that from this term over here, it consists of it's a likelihood term which consists of both the latent and the observed random variables over here. But in the case of the chain CRF, where it becomes a conditional random field, we actually model the interactions between all the observed random variables here. Now, what's interesting here is that we directly model the posteriors of all the latent random variables together with the observed random variable. Hence, this guy here becomes a discriminative model. You can see that the hidden Markov model and the MRF suffer from what we call the labels bias problem, because we do not model the relation between all the observed random variables in these two cases. What this means is that the local feature at time t do not influence the state that is prior to time t. In other words, if we suppose that we condition upon what we have observed in this case over here, then all the random variables that are preceding y2 would be de-separated or will be decoupled. It will be independent, conditionally independent from y3, for example. And it's similar for this case over here. Once we observe this, since this is a head-to-tail structure, that means that everything that is preceding this, including x2 over here, it would be conditionally independent of x3. What it means is that when we do inference on y3 or on any state of yt, the only random variable that we take into account would be the latent random variable that is preceding this particular random variable here at time t. And this is not good, because what it means is that when we do inference of every latent random variable here, we would not have a global knowledge, or we do not have the global context of the model. An example here is that consider a part of speech tagging task where I see the word of banks over here, and I want to tag it as either a noun, or that means that I want to assign the latent random variable to be either a verb or a noun for this observation over here. So in this case over here, since we are conditionally independent of all the other random variables or all the other observations upon observing this particular guy over here, this means that we are only dependent, we are only looking locally at this observation as well as the previous latent random variable. And it makes it hard to distinguish between whether this word bank could be a noun or a verb, because in fact this word banks, it can be both noun and a verb when it's used in a daily English context. Without knowing the global context of the whole sentence, it becomes ambiguous. But in the case of a conditional random field, we have a global knowledge. That means that we see all the others when we take into, or when we do an inference for every part of the text. We take into account of all the observed random variables in the whole sentence. So suppose that we say that we see the word fishing in the later part of the sentence, then this banks is going to become more likely that is referring to river banks, which is a noun, compared to if we observe money in the later sentence. It could mean a verb, that the person he banks in some money into the account, for example. So this means that the problem here of the loss in the global context is alleviated in the conditional random field. Here's an example of the use of Markov random field where we have a video of ants moving in the scene, and we want to track every ant in the scene. I'm not going into the detail. If you are interested, you should read this particular paper here. But probably in this point of time, you are not able to understand the inference of this because it's going to make use of what we call the MCMC sampling to do tracking. The objective here is that we want to, for every ant that moves in this video, we want to track that particular ant, and there is a certain interaction. So based on the what we have observed over here, in this case, the Z is the tracklet, the green boxes that is output from an ant detector, and X here tracks the current location of every individual ant over here. So we can see that the current location is dependent on the previous location, and this can be further factorized to include the interaction between the ants in the scene. So XIT and XJT represents all the neighboring ants in the scene. They better not collide into each other. Hence, there's a local potential clique over here. In addition to the current location is dependent on where the location of the ant in the previous frame. Here's another example that makes use of a conditional random field to model the road segments of the center lines of the roads from area images, for example in Google Map or OpenStreetView. So in those cases, the center of this road is often mismatched because it's really very labor intensive to draw all this into the scene, and there is often a mismatch from automation algorithms. So the idea here is that given the prior observations of the road, for example, inputting these error images, I'm going to train a classifier. It could be a deep network that tells me which pixel belongs to the road and which pixel doesn't belong to the road, for example. And then I would have also some other detectors such as the car detectors and the appearance context on whether this is an edge or not. So these are the likelihood information that is encoded from the classifiers that we can pre-train using some other methods. And here, what we want to do here is that we want to take into account all of this observation as a likelihood term into the final inference of the road segments in from these observations over here. And we want all these road segments to be smooth. That means that each one of the segments, it should be continuously smooth throughout the whole entire road, as well as we also want them to overlap well with the observations. And in this case, we can model it using a conditional random field. I won't go into the detail of the inference and the detail of the papers, but hopefully by the end of this semester, when you look at this paper, you will be able to understand what's going on inside here. Here are some results of the from this particular paper. We can see that it's giving a very accurate road segmentation or road labeling of the scene. So finally, in summary, we have explained the concept of Markov properties, in particular the global, local, and pairwise Markov properties, and use it to find all conditional independence in an undirected graphical model. We have seen that this is much easier than the directed graphical model case, because we have shown that the global, local, and pairwise Markov properties, they are equivalent to each other, and we simply read off the conditional independence by looking at the truncation of the paths from any nodes to another in the undirected graphical model. And we have also defined the Clique potential functions, in particular using the Gibbs distribution and the log linear model to parameterize the joint distribution of a Markov random field. Finally, we look at the differences and similarity between a Markov random field and a conditional random field, as well as the advantage and the disadvantages between the two of them.